this is a fairly easy question if you do not commit one mistake. Over here in this question, we have two masses M and M hanging over a pulley, but the only change in this question is that this pulley has some mass. Its moment of inertia is given to be I and its radius is R. So remember always one thing, that the tension in a one particular string always remains the same only if the string is massless and the pulleys over which it passes are massless. In this case, the pulley is not massless, therefore the tension in two strings will be different. The only mistake students do in this question is that they assume T to be same in both the parts and then they get the wrong answer. So in this question, after assuming T1 and T2, we write the equations. Since this is going down with acceleration A, this will go up with acceleration A, because this being a string, we can apply string constraint. L1 plus L2 is equal to constant. L1 double dash plus L2 double dash is equal to 0. Now what is L1 double dash? L1 double dash is the rate with which the distance between this pulley and this mass changes, that is plus A. Plus, let this be A dash if, then L2 double dash is equal to rate with which this distance changes. Now this pulley is at rest, so it changes only because of this mass, that is equal to minus A dash equal to 0. Therefore we get A is equal to A dash. We could have done this directly also. The acceleration of this mass is A. Now we write the equations in vertical direction for this mass to get mg, capital Mg minus T1 is equal to Ma. On this mass we get T2 minus Mg is equal to Ma. Now we see that we have three variables, T1, T2 and A, but we have only two equations. So we need one more equation to solve the answer and get the solutions for all the values T1, T2 and A. So the third equation which we will get is from the pulley. Now we know that the rope is not slipping over the pulley. The rope is not slipping over the pulley. Therefore, the acceleration of rope and the point of the pulley to which it is attached will be same. Therefore, for the pulley, let the angular acceleration of the pulley be alpha. So the acceleration, tangential acceleration of any one of its point is A into R, alpha into R. Therefore, A is equal to alpha R. We can write the acceleration of this block is equal to alpha R because the acceleration of this block is A, means the acceleration of this string is A, and the string attached to here is not slipping relative to the point of pulley here. Therefore, the acceleration of this point of pulley is equal to the acceleration of string, that is equal to A. Therefore, we can write A is equal to alpha R. So we get this relation and we write the equation for the pulley. For the pulley, we write the net torque is equal to I into alpha. The net torque on the pulley is equal to, the pulley is pulled by T1 here and T2 here. So the pulley, the torque due to T1 comes in the outward direction, that is equal to T1 into R minus T2 into R, because the torque due to T2, it comes in T2, it goes inside, therefore the torque due to T2 comes in the inside direction. We write this as I into alpha. Net external torque is equal to I into alpha. I is already given. We can write this alpha as A upon R. So this is our third equation. So we get three equations and three variables. So we have three linear equations, 1, 2 and 3. By solving these three linear equations, we get the answer for A to be m minus m into g r square upon I plus m into r square. So this is the final answer for the acceleration of the blocks m downwards and m small m upwards. This was found out easily if you know the fact that the tension in the two strings are different.